My name is Tatjana.
My name is Marijana.
We are coming from Serbia, from a small town called Kuzmjak, where we attend primary and secondary school Petro, Kuzmjak, which is the unique school, the only school in the world where students learn in Romanian language.
In our presentation, the expedition that bridges the gap between material science and mathematics, we will show you how mathematics can be applied in science. Specifically, the part of science we were interested in was material science.
Material science is an interdisciplinary field which studies the properties of materials and their application in many areas of science and engineering. It covers of understanding how materials can be created, used, changed, and improved, and how they react under different conditions. For instance, under different mechanical influences, as well as changing temperature or pressure.
This specific branch of science is very useful and important because we constantly use materials in our everyday life. For instance, we know that pencils are made of wood and that this laptop is made out of plastic. Materials are also the basis of high technology. They are used in biomedicine, production of computers, televisions, solar panels, and many more items that we use every day.
When we observe properties of materials, we observe many different parameters. One of the main parameters that material scientists observe is called activation energy. Activation energy represents the minimum energy that needs to be provided to the reactants in order to start a chemical reaction.
One famous Swedish scientist called Svante Arrhenius was especially interested in this subject. Even though he was originally a physicist, he was often referred to as a chemist and was famous for being one of the founders of physical chemistry. He proposed the Arrhenius equation, an equation that can be used to mathematically describe activation energy. And this is where material science and mathematics collide.
Arrhenius equation is a mathematical model that describes the dependence of the rate constant of a chemical reaction on temperature or activation energy. It is, as you can see, in the form of exponential function. In this equation, K represents the rate constant of a chemical reaction, A is pre-exponential factor, R is universal gas constant, and T is temperature. EA represents activation energy.
We made two graphs in GeoGebra, an educational software that we use in our math class to show the mentioned properties. Here we can see the dependence of the rate constant of the reaction on activation energy. We have the activation energy on the x-axis and the rate constant on the y-axis. And it can be noticed from this graph that when activation energy increases, the rate constant of the reaction decreases. On the next graph, we can see the dependence of the rate constant of the reaction on temperature. Here we have the temperature on the x-axis and the rate constant of the reaction on the y-axis. And it can be noticed from this graph that when the temperature increases, the rate constant of the reaction also increases.
On this slide, on this video, you can see the simplifying of Arrhenius equation to make it more suitable for activation energy calculations. Our equation we transformed with the help of logarithm, and since we know this property of logarithm, we can write our equation like this, in this form. And since we know that natural logarithm of E is 1, we can write our equation in this final form. As in this final form.
We can see that Arrhenius equation is now in the form of a linear function, a function whose graph is a straight line. In this obtained form, the natural logarithm of k is the dependent variable, 1 over t is the independent variable, then the natural logarithm of a is the y-intercept, or the place where the line crosses the y-axis, and EA over r is the slope of the line. Knowing the slope of the line and the value of the universal gas constant, we can determine activation energy
material scientists use more sophisticated models such as Ozawa-Flynn-Wall and Kissinger-Akahira-Sunose for determining activation energy. These models are based on Arrhenius equation, and with their help we can determine activation energy by measuring the temperature of under controlled heating rates in complex material scientists experiments. On this slide you can see Kissinger-Akahira-Sunose model. In this model, beta represents heating rate, alpha of G represents function of the reaction model, and T represents the temperature of the maximum speed of the reaction. R is universal gas constant, A is pre-exponential factor, and EA is activation energy.
Using some simple mathematical operations, we can transform this model to make it more suitable for calculating activation energy. In this obtained form, the natural logarithm of t squared over beta is the dependent variable, 1 over t is the independent variable, and EA over r is the slope of the line. Knowing the slope of the line and the value of the universal gas constant, we can determine activation energy even using more complex mathematical models.
You must wonder where we found out about all these interesting things. Together with our math professor, Natalia Budinsky, we visited the Faculty of Forestry at Belgrade and Faculty of Technology at University in Novi Sad. The goal of our expedition was to research about mathematical modeling. Mathematical modeling is a process of solving real-world problems with the application of mathematics. We were seeking for the bridge that links the visible world of materials and invisible world of mathematical formulas. At faculty, we had chance to talk to scientists that work in the field of material science with the application of mathematics, and we participated in the measurements where we collected the real-world data from the experiments.
The experiment that we participated in was about examining how different types of wood affect the properties of urea formaldehyde resin. 3 different types of wood were used for the comparison: fir, poplar, and beech. There were made 4 samples. The first sample was pure UF resin. The second sample was UF resin in combination with beech. The third sample was UF resin in combination with poplar. And the fourth sample was UF resin in combination with fir. These samples were processed under different heating rates with the differential scanning calorimetry method, and temperatures of the maximum speed of the reaction were measured. We can see the results in table 1. We can see the heating rates that were used in the experiments and the temperatures of the maximum speed of the reaction of UF resin alone and in combination with beech, fir, and poplar.
On this slide, you can see Kissinger-Akahira-Sunose model that we made in GeoGebra. In this model, we observed values of natural logarithm of beta over t squared, which is in this model represents dependent variable, and we put these values on the y-axis, and we observed the values for 1 over t, which is in this model independent variable, and we put these values on y-x-axis.
And that was the model of UF resin alone. And this is the model of UF resin in combination with beech. And here A is the slope of the line. This is the model of UF resin in combination with fir. And A is the slope of the line again. And the model of UF resin in combination with poplar and the slope of the line. For all of the samples, and these are the results. We can see the slopes of the line and the calculated activation energy.
The final conclusion is that there is no meaningful differences on activation energies for observed samples. That means that when we use UF resin with combination of wood, particles provide the same performances as when we use UF resin alone. Mixing UF resin with wood, particles can diminish the cost of the production and save environment as well. All can agree that these results are very interesting and useful.
And these results and this research are especially interesting and useful to our local community, since wood industry is highly developed in the town where we come from. Thanks to the help of the local wood entrepreneurs from our town, we got a chance to come here and present these results and this research and show how mathematics and science are building a common future. Thank you for your attention.
Do you have any questions? No.
Okay, so we would like